Okay, we're now going to turn our attention to single slit diffraction. And the way that I'd like to introduce this is again with the mechanical analog. In this case here, hopefully this will answer maybe a bit of a mystery that you may have seen if, say, you'd ever traveled along Michigan's coast. As you go along the Great Lakes, you find that as you go through no end of tiny little tourist towns, you'll have the state highway going through like this. Now, off to the side, over here, so we'll have some shore here, and then the Army Corps of Engineers will have built a breakwater to help protect shipping going in and out of the village, like so. And if you take a look, usually somewhere around about here to here will be the public docks. And here to here will be some private boat club's docks. Or they might be flipped, but usually it's something like that. And then in the middle, along through here, there's usually a village park. Often in dead center of the village park will be the Soldiers and Sailors Memorial. Honoring all the veterans who came from that town. And then usually sitting off in the corner right around here will be a little hobby horse on a little cement hobby horse on a giant iron spring that was put in by the Optimist Club in the 1950s. Now, over here it'll depend whether there was a economic revitalization that had happened or not, but generally speaking there's going to be some if let's say that there has been an economic revitalization, if that's the case, there's going to be some sort of a kitschy strip mall here. That will sell overpriced arts and crafts goods, maybe a little bit of beach stuff, maybe, and there'll probably be a coffee shop or something like that in there, and maybe a place for some pizza. Up over here, there will be the Dairy Twist, and it is always a Dairy Twist, right? Right over there. Actually, I take it back. It's going to be over here so that the kids who are playing on the hobby horse can run across the street and buy the ice cream. And then usually somewhere up around over here is going to be the Dollar General. All right, so now why is pretty much every Michigan tourist coastal town laid out like this? Well, it turns out it has to do with the pattern of the waves that's coming off of the breakwater. So let's say this is, it doesn't matter which Great Lake it is. Let's say this is Lake Huron here. So we have waves that are coming in here. And if you take a look, what you'll notice is that coming off at a bit of an angle off the breakwater, right here and here, there will be no waves at all along this line. And then there will be very light wave action here and here. And by light, I don't mean electromagnetic radiation. I should say quiet waves or low intensity waves. here and here. And then you'll have regular wave action here. Now we'll get into the mechanics of how this works, but it'll turn out that the wavefront, that wavelets being, following Huygens Principle, wavelets being emitted from the wavefront will interfere with themselves in such a way as to create this pattern. So they put docks everywhere they can to keep the boats from pitching up and down too much, but what do you do with the land in the middle? Well, I guess you may as well put a park there. So they go ahead and stick the park there. Well, since you got the park there, people are hanging out for the beach. That's what drives locating the strip mall, the Dairy Twist, and the Dollar General. So there you go. Now, why does it work this way? And again, it doesn't matter if it's a mechanical wave like a water wave or if it's light, but here we'll go ahead now and start to take a look at light. So I have greatly exaggerated here, just a single slit, and I have a plane wave of light coming, into the single slit. Now right here, let's look at this wavefront right here. Let me make that a different color so that we know that we're talking about a wavefront. There we go. Now, what what Huygens Principle says here is every single point on here is a source for wavelets to propagate forward. So let's look at this point here, and then this point here, 1/2 of the thickness of the slit down there. If I look over here, so let's say this is the central axis like so. This, if I look at this path here and this path here, this wave, I can construct it so that at this angle theta, this path is 1/2 of a wavelength longer. So if a crest was arriving from this wavelet here, a trough arrives from this wavelet here, gives us destructive interference, and this is our first minimum. Now, that is only true, though, if it turns out that you have to say, well, yeah, but we just looked at two wavelets. This wavefront is a source of, every single point on here is a source of wavelets. But it turns out that you can always match them. Again, I picked two of these 1/2 a wavelength apart. And it'll be exactly the same deal. The longer path will be 1/2 a wavelength longer. And I could do this with, say, still yet a different one here. And it's matching one exactly 1/2 a slit width down there. And again, it's the same deal. The lower path is 1/2 a wavelength longer. A little tedious to prove this in general, but it's true and it does work out. So for every point here, at the first minimum, for every point here, there's a matching point 1/2 the thickness of the slit down here that will be giving us the wavelet that will destructively interfere. So there's still, if I look in dead center, there's still a central maximum here because my points will constructively interfere in the middle. So what you end up getting is you'll have a central max like this, and then some additional weaker maxima heading on out. So, and it turns out that in single slit diffraction here, with the exception of the central maximum, wherever you would have had a crest in a Huygens experiment where you had one slit here and one thin slit here and one thin slit there, you end up with a trough in single slit diffraction. So the result here is to locate the minima. The pth minimum will be equal to p lambda over a, where a is the width of my slit. Or if I'm locating it on a screen, the location of the pth minimum will be p lambda L over a. Where p here is not momentum. It's just a number, 1, 2, 3, whatever. That's the order of the minimum. And to give you some sense of what this would look like, this is a single slit interference pattern for where I had red light passing through the single slit. Now, this slit is wider than the slits that I was doing when I did something similar with Huygens experiment. Basically, the width of this slit is roughly what would have been the separation of the two slits in Huygens experiment. So that's for red light. Now, if we remember that blue light has a shorter wavelength, would you expect that if I repeated this experiment for blue light, would you expect that the dark fringes would be located closer together or further apart? Go ahead and pause the video and get back with me on that. So it turns out that the fringes will be closer together. Sorry for the quality of the picture. I did the best I can. Feel free to scrub back and forth along the timeline here to compare the dark spots in the blue picture in it with blue light and with red light. Now, you might be wondering what's happening vertically. It's, again, literally the same deal. It's just happening vertically instead of horizontally. But we're just focused on the horizontal bit here. So you'll also remember when I showed you this pattern in a previous video, this was for double slit diffraction, and I pointed out at the time that you could see that there were basically missing bright fringes. And this is because even though the slits are thin, they do also act as single slit interference. So you have a single slit pattern superimposed on a double slit pattern. Now, because the width of the slits in the double slit experiment is very narrow compared to the single slit experiment I showed you, that means that the location of that first minimum is quite far out. And so that's where you see the dropouts at the edges of the picture, that's where the first minimum from the single slit pattern superimposed on top of the double slit pattern. All right, so let's go ahead and try making this a bit concrete again with some numbers here. So let's say that I want to find the wavelength of light when we had the second minimum of a diffraction pattern from a 0.1 millimeter wide slit. And the second minimum occurred at 0.70 degrees. So let's go ahead and figure out what the wavelength of the light would be there. So again, remember we locate, as long as the angles are small, and 0.7 degrees is definitely small, we said that theta p is equal to p lambda over a. Here I'm solving for the wavelength, so that'll give me that lambda is theta p a over p. Now, I have to be a bit careful when I plug in the numbers. I can't just willy-nilly substitute in 0.7 degrees. And that's because these angles need to be in radians. So you have to remember that there are pi radians in 180 degrees. And we said the width of my slit was 0.1 millimeters. So we'll say that's 0.1 times 10 to the negative 3. Remember, the milli prefix means 10 to the negative 3 meters. And then we said that this was the second minimum. So the order is 2. So that's going to give you 6.11 times 10 to the negative 7 meters, which is 611 nanometers, which is square in the visible light range. So that seems like a very reasonable answer. And this is one way that you could measure the wavelength of light, although in practice you're more likely to use Young's experiment or a diffraction grating, which we'll get to in a moment. I do want to spend just a quick moment, though, talking about circular aperture diffraction. Just because this is something that will come up when we think about the limits of resolution of things like our eye or a camera lens or a telescope or anything like that. The optical elements tend to be circular. And it turns out that it's going to be the same sort of idea here. So now instead of this being a slit, this is a hole, a circular hole. Circular hole. And we'll say that the diameter of the hole is d. Now, if I look at this, so my screen will be over here. And what I'll get is I'll get a central maximum, like so. With progressive dark fringes off. They won't be evenly spaced. And if I were to look at it, say, like this, so looking at the screen this way, what you'll get is a bright spot in the middle. First dark fringe, then a bright spot, then another dark fringe, another dark fringe, and so forth. Now, usually we don't get too strung out about these peaks here. They tend to be a lot less intense than the central max. So we're usually interested in what this angle from the center of the peak to the first minimum is called. So that's the angle for the first destructive minimum. And the argument is the same kind of idea, but you have to find matching sources of wavelets on different parts of the circular aperture, and the math to come up with it is absolutely god-awful. but you end up getting that in radians, the angle, the first minimum will be 1.22 lambda over d. Now, unfortunately, the second minimum won't be 2.44 or anything like that. The numbers are just weird and you have to look them up in tables, but this is the main one that we're worried about, because this is going to tell us what is how small can we possibly resolve an image. The way I like to think about how big this spot is going to be is simply how many wavelengths can you fit across the hole. The more wavelengths that you can fit across the hole, the bigger the angle that the fewer wavelengths you can fit across the hole will mean a bigger wavelength, which will mean a bigger angle. So if you can't fit very many waves across the hole, you're going to get a big angle and you won't have as sharp of an image. This is why, for instance, images from radio telescopes are always going to be of poorer quality than from, say, telescopes working in the ultraviolet or the X-ray or something like that. But we'll get more into that in later videos. All right, in the next video here, we will go and take a bit of a look at diffraction gratings and see how they apply to spectroscopy. Catch you over there.